Good afternoon, all. So today I'll be presenting this work, effect of simultaneous FDI and DOS attack on multi-area power system with dynamic event triggering algorithm. So these are my outlines. Introduction, multi-area power system design, system with attacks, how to model those attacks and integrate those attacks into the system. Steps to find this resilient controller. We'll be discussing results and discussions, and then we'll conclude with some future scopes and with reference. In this decade, we have moved on from conventional grids. With introduction of information and communication technology, we find timely and reliable data at the control system, which will be again helpful in deciding this generator control input. So the sensor data from the field, like frequency, voltage, and talent power deviations, will be fed back to this control system, and the control system will be taking required control action, and those actions will be communicated to this field devices like actuators. So this communication part in between, like this whole power system, will be impacting this complexity and will introduce privacy issues. So recently from 2020 you can see a frequent trend of cyber attacks in power systems. Like in 2021, US experienced a cyber attack where Texas energy market was attacked. Ukraine again after 2015, we again find this attack on energy company which disabled many facility of power utilities. So nowadays cyber attack are becoming more common, and so we should find some resilient controller which will be resilient enough for these attacks. Here the multi-area power system will be designed as state space equations. These areas, individual areas, will have 5 states. One is governor power deviation, turbine power deviation, frequency deviation, dial and power deviation, and area control error. Area control error comprising of frequency deviation and dial and power deviations. So these signals will be sent to the control center to decide upon this generation changes. Here the event triggering systems, namely ETS, will be triggering for only the necessary samples which need transmission to the control center for required control actions. The unnecessary data, when there are no load deviations, will be ignored and not triggered to the communication network. So we are saving the bandwidth in the process. So this control actions will be again depend upon this control gains which we will be designing in our problem formulations. The controller input to the generators will be decided based upon the area control error and the controller gain K. The controller gain K will have two effects. One is integral effect, one is proportional effect. Again, for event triggering system, we'll have omega matrix which will reflect how much states effect will change the ETS algorithm. The phi of t is a dynamic parameter which can be a static one like a scalar or a dynamic trigger one. So for the static one we will assign a scalar value, but it cannot accommodate the state dynamics properly. So in recent works and for this work we are considering dynamic triggers which will be changing according to the states, and the event triggering will be more frequent when the error between the previous sample and the current dynamic state of our multi-area power system is more. So more the error, more number of samples will be sent. In the presence of denial of service attack, no communications is possible, which is represented in figure 2. The resilient event triggering signals will only be possible after this denial of service attack, where these false data injections are based on probabilistic model. Those will be occurring with a probability with a probability less than some tolerance limit. Let's suppose 5% of time it can occur. The overall model of the system is represented in equation 5, where the effect of denial of service attack and the effect of FDA attacks are modeled. So for the flow, we can start with giving the state equations and the DTP equations. Then we have designed how to accommodate this denial of service attack and false data attacks to these state equations. We will be formulating the Lyapunov-Kravosky functional, which should be accommodating this dynamic of time delays and this FDA attacks. Upon solving for stability, we will get through some linear matrix inequalities which needs to be solved using MATLAB. For our work, I have used Mosaic solver, where we can get this controller gain value and the DTP weight matrix. The sample time is selected as 0.01 seconds. The denial of service attack is modeled as a periodic signal of time period 5 seconds and turn up time period is 4.95. The false data injection probability is chosen to be 5% and the signal is to be a tan S function. The load change starts from 0 seconds and is modeled as 0.4 per unit magnitude decaying with time. So these parameters will be used and will be solved using Mosaic solver in MATLAB. The LMIs will be solved and we can get this controller gain K and this weight matrix of DTP as the following. So from this 0.3a we can find the states responses are settling at 28 seconds and they are coming to normality. So this control inputs are also settling for the three areas. From the figure C, 3C, we can find that this release time will be lesser. That means more and more samples will be sent more often when the state dynamics is changing drastically. So for initial period like from 0 to 10 seconds, the triggers are more, hence the release period is less. When the state response settles, the samples will be sent less often, saving the network bandwidth. That will be necessary to ensure that the bandwidth remains to the lowest. The progression or the evolution of the DTP parameter phi t is shown in figure 3D, which shows the changes in the period 0 to 10 due to drastic change in states. The false data injected in this scenario is plotted in figure 3E, which shows a tangent function with respect to the output from this multi-area power system, which is also settling. From this figure 3C, we have found the trigger to be 549 triggers, which is less than 5000 samples, because for 0.01 sample time, we'll get 5000 samples for 50 seconds, which shows our effectiveness of our model in reducing bandwidth use. The effect of parameter variation is studied in this figure 4. We will be changing denial of service attack, turn off period time, DTP parameter, and the probability of FDA attack. When there will be a settling value in the state space equation with tolerance limit below 0.1 for moving averages of 100 samples, we will say there exists a solution. Each solution is represented in one dot. As you can see from figure 4, for more critical turn-off period like 4 seconds, there will exist fewer solution space. Similar goes with high value or high probability of FDA attacks. We have model for the multi-area power system, and there's attacks like denial of service attacks and false data injection attack. A resilient controller is proposed which found to be effective enough in eliminating those attacks. Further, we can go in the direction of accommodating more nonlinearity like GRC, governor rate constraint, deadbands. We can also accommodate some amount of modeling error, some level of packet drops in the communication network, and more complex attacks like coordinated attack and state dependent attack can be studied. Scenario. These are my references. Thank you. If you have any query, you can contact me through this email or in the QR code of my LinkedIn. Thank you. Have a great day.